And instead of evaluating exponential of A, what I really want to do is exponential of A times t. So just a slight modification of this definition. So, how does that work? So if that's A, some scalar t times A is just going to be t times the multiplication. So you get t times lambda, t, 0, t. So that's t to the a to the power of 1. What does that pattern look like if we keep raising the exponent? So ta squared is just this matrix times this matrix. Right, simple 2 by 2 multiplication, and then you know how to do this. So this is simply t squared lambda squared, t squared lambda plus t squared lambda, 0 t squared lambda squared. So if I keep doing this to the cube, to the 4th, to the 5th, you develop a pattern that you can confirm. So all the way to the, let's say, k phase, you can confirm that you get something like this. T lambda k, k t lambda, lambda to the k minus 1, 0 t to the lambda. So third power, fourth power. So now, I know what ta to the k is, therefore I know what ta to the k over k factorial is, and therefore I know what exponential of t times k. So therefore, exponential of ta, which is really the quantity I want. Yes. Maybe it's not t to the power of lambda. Maybe it's t to the power of k. So, just by evaluating that definition, taking the exponential now of each entry, we know how to do this. So you get, as we saw last time, very interestingly, you get each entry in this matrix is an infinite t. T lambda to the k over k factorial. I should make this bigger. I will not close the braces until I'm confident that I have enough room. T, k equals 0 to infinity. T lambda to the k over k factorial. You will get 0 here. And once again, k equals 0 to the infinity. T lambda to the k over k factorial. That's a big number. And of course, you know each one of these power series what they are because they're just the exponential. So this becomes exponential of t times lambda, t times the exponential of t times lambda, 0 exponentials of t. So I could have started with this instead of having you laboriously go to the second dimensional cases of the matrices, because this is applicable to any dimension. But I wanted you to get a flavor for what we're going to do later, so that's all. But anyways, I'm not done. But this is the answer. Okay, this is the explanation. Okay, so what though? What difference is that possibly? I need my list. So we know how to do this exponential of a matrix. It's just taking the matrix to some power and applying the infinite series that you know from your calculus. So that's great. But let me augment this now with some further properties. Okay? So let me give you a proposition. Namely the following. So if V, let's say some vector in Rn, and call this an eigenvector, I've been told that I should write bigger. So I'm trying my best, but it's not easy. Associated to lambda are eigenvalues. Then my claim is that V is also an eigenvector of the exponential of the matrix associated to the eigenvalue e to the lambda. So if V is an eigenvector of A, then V is also an eigenvector of the exponential of A, associated to e to the lambda. And I can prove this to you very simply. I don't want to spend too much time on proofs, but things we can do in 1 or 2 lines, we should do. Oh, the proof is very simple. If in fact V is an eigenvector of A and lambda is an eigenvalue, then it must be true that A times V is equal to lambda. That must be. But then that implies that the exponential of A times V, which is the quantity that I'm interested in computing, I can write this, if you remember from your calculus, as the limit as n goes to infinity of the following expression. K is equal to 0 to n. AK V over K. That's an alternate way of specifying the exponential, if you remember it from the Okay. But I know what A to the K times V is, because that's just the eigenvalue relation. So I can write this as limit as n goes to infinity of what? Still the same summation, but now I have lambda to the K over K factorial times V. I don't know where the extra lambda came. Probably because I don't know how to. But then now the summation is just over K, so I can pull out the V of the summation. So this is the same as Singh. And I will also now take the limit as n goes to infinity. So K is equal to 0 to infinity, lambda to the K over K factorial times V. And what is this equal to? Exponential. So this is just exponential of lambda to 10. And that's it. Simple one line. So indeed, if V is an eigenvector of A associated with lambda, then V is also an eigenvector of A exponential. Because we get this being equal to okay, let me give you one other proposition, then I'll state the main result. You can tell I'm losing my patience with linear systems. I want to get rid of it. Okay. Proposition. This is the key one. My claim is that the time derivative of this exponential matrix, so d by dt of exponential of t times a, my claim is that this is equal to, as you can imagine, a times the exponential of ta, which is also equivalent to. In other words, you can write the matrix multiplication in it. That's my proposition, that's my claim. And I need more paper. I will not prove this to you because it's a very easy proof. But it's in voice in 2-3 months, so you can actually see it. It's one of the few things we're doing that's actually in your textbook. So proof. Another one-line proof, or maybe 2 lines. In voice and deep. I think chapter 7. But that's the key result. And it's analogous to taking the time derivative of just any old exponential function. The constant just comes. I've dropped 3 pieces of chalk since I started. But it's not good. Okay, so we have 2 key propositions. We can finally state the main results that I should have started with 2 weeks ago. But as I said, I had some hidden motivation. And that goes as follows. Okay. Theorem. One can say this is the fundamental theorem of linear dynamics. So I'll put here. Fundamental. And it goes like this. Let A be any n by n matrix. So 2 by 2, 3 by 3, 4 by 4, whatever. The solution to the initial value problem, IDP, with initial condition x of 0 is x naught, is simply the following. Is x of t equal to the exponential of t times a, which is why I fussed about computing this quantity, times x naught. That's the solution. So, any linear system you're given, the IDP of course, x prime is equal to x. So that's the situation we always have started with, but so far I've been doing 2 by 2 cases. And then I go to the plane of computing the eigenvalues, eigenvectors, but you don't have to do that anymore. Because now we know what the whole answer is for any dimension. So it's the exponential of the matrix times the initial matrix. That's the answer. And my claim is that this is the unique solution. And in fact, the proof of this I will do because it's illustrated. Okay. The proof is very simple. It simply requires us to use this proposition. Okay? So, from the previous proposition, we know that d by dt of exponential t times a times x0, just by this proposition, must be equivalent to x0 times d by dt of the exponential. But then by the proposition, I know what this is. So this is just a times the exponential ta times x. Good. And of course, so finally, since we know what this quantity is, since exponential, let's say of 0 times a, is just or times x naught. What is this quantity equal to? What is exponential 0 times a times x0? Very good. So we satisfy the initial conditions. So this is the solution. We take the time derivative, that's what we get, which is equivalent to the right hand side. And indeed, it satisfies the initial condition of t. So we have a unique solution. That's it. I could have done this in one class, the linear systems case. But for some reason, I thought it's a bit weird to start with the exponential of a matrix. So I wanted to introduce you to.
So,
Question.
sorry, so in the linear, you give
as long as you go through the labor of computing the exponential range. But this is the right answer. This is the way you should do it. But sometimes, I guess, it depends on what problem you're given. Sometimes maybe it is easier just to find the eigenvalues. If you're in 2 by 2 matrix, it's sometimes easier just to write down there. Especially if it's diagonal, you know what they are. But you should note that even in that case, when we're finding eigenvalues, it's always exponential t times eigenvalue. So they're the same. You can see it's the same. We're done with linear systems, okay? Now I will go through the nice part of the course. Not non-linear systems. But I need to introduce many things in this nice advanced group of students, math major, much better than the engineers. One more to do. No. I need to go back though 1 second and talk about the idea of flow again. It's very important. So now, I want to study, once again, vector x prime, but not equal to ax anymore. Now, generally, just vector x. So, this is a general system. It can be linear, nonlinear, whatever. And before, up to now, I've been dealing with the case where f is equal to a times x. So no more. So it's a dynamical system. This is what we do. But even in this deceptively simple thing I've written down, there's a lot of machinery behind it. One of the examples is time. The solutions, as you saw even in the linear case, evolve in time. But what does that mean? So, evolution of a dynamical system. What does that mean? It means that there's a change in the state of the system with respect to time. So you have some system that's in some state, and at some other time, it's in some other state. So that's what we mean by evolution. But I should be more precise about what I mean by that. What do I mean by evolution? Not the biological version, the math version. Although the two concepts are surprisingly related. But biology is, people are always aloof to that. I don't know. Well, I do know why they don't do math. Okay. What do I mean by that? I mean that given initial state, for lack of better terminology, let me call it x0. It's your initial condition. Vector. Remember, my vector means power. We want, so if you give me just an initial state, I want to figure out what the state of the system will look like at all future times, just from knowing the initial state. But is it good enough just to know the initial state? What am I missing to figure out what the state of the system will look like at a future time? More specific than that. I need something that will act on my initial state to give me the state of the system at some other time. I'm missing something. Somebody said. Flow. Right. Why? I want, okay, let me read. We want an evolution law. That determines the state, let's say x sub t. So given an initial condition and an evolution law that I apply to this initial state, I should be able to tell you what the state of that system will be at some future. So I need both pieces of information. But then we know what this evolution law is because you know what it means to carry a solution from one state to another. And what is that operator? It's the flow. That's why I introduced it. Okay. And this operator is once again my phi t. I will explain it. And basically, how does this work? So my system at some future time, xt, is found by applying this flow operator to my initial state. This applied to that will give me the system at some future. So I have to know what this is. Again, and this phi t, for a bunch of t's, so I put that in curly braces. I mean a family of phi t, is what you called last time. So when you are doing dynamical systems, really what is happening is that you give me an initial condition. You give me the evolution law, which is the flow operator. It acts upon the initial state, and it gives you the state of the system at some future. I'll make it more. Let's see if I can make this a bit more clear. So, some properties of this flow operator, which I'll just write phi because I don't want to draw it braces. The first proposition is that phi at time 0 should just be the identity of. And if you remember from your calculus course, idea of x is just x. That's what you meant for identity function. The second property is the following. Phi, so you start at phi t. Phi t plus s is some s time ahead of t, right? If my system is state at phi t, then phi t plus s is some future time. So the future time evolution of my system, which I denote as phi t plus s, should have this property, namely that phi t composed with phi. This will be clear in one second. So then, when I apply phi t plus s to my state vector, which is x, what do I get? By this, it's just the composition of the two functions. So in this situation, it's just phi t, phi s on x. Because you know what the composition mapping is. But then what does this mean? Let's draw it up. What does this mean? This means the following. So let's say, just in some general sense, this is my plane or base portrait or something like that. If I start from x0, my initial state, and I want to go to my final state, which is xt, and in between these two I stop at some intermediate state, let's say xs, this means that the evolution is completely deterministic. I can obtain xt from xs, or I can also obtain it from xt. That's what I'm saying. So it's a composition. You can get from your initial state to your final state either by going straight or by a composition of time. So what I'm saying is that this evolution then is completely deterministic. That's what I'm trying to say. This evolution is deterministic. And obviously to go from here, I apply phi s, and to go from there, you apply phi. What do I mean by deterministic? means that if I know the initial state, and I know the evolution operator, I know deterministically exactly what the state of the system will be at any future. If you have stochastic variations, then we need to do a whole different course. It's called Stochastic Differentiation. We will do that next year. I won't do it, you will do it. But all of physics, most of biology, rely on this idea. It is deterministic equations. So Newton's equations, deterministic. Maxwell's equations, deterministic. Einstein's equations, deterministic. That's why physics is physics. It's laws of nature. So all laws of nature are deterministic laws of nature. The idea is that, once again, if I give you initial state, and I give you the evolution law or the equation, you can tell me what the future time is, or the future state is at any specific, because it's deterministic. So even in our case, our linear system, the flow in this case is just x naught. So the idea is, you know, if I apply this now to some future state, you know what the future state of the system will be. Because you know the evolution law and you have an initial condition. So it's the same thing. So that's the ground we are on now, on this. And any questions about this? The more interesting question now is, which I won't get into too much, but if I give you a final state, can you tell me what the initial state of the system is? So if I give you just a final state and I ask you, what did this state look like initially, can you do it?
I can do it.
You can do it for a linear system, but in general it cannot be done. Because it could be that your flow, if you remember, it could be that it's not inverse. The inverse is not inverse. So it's much harder in nonlinear systems to construct the initial state from the ground, which is a huge problem in cosmology. Anyway, so does everybody understand this in principle? No. All right. So I'm surprised though. Let me go back to what I wrote down. I'm surprised about something that nobody brought up. Even Gates has been silent on this. He wasn't thinking. When I wrote this down, or even when I wrote down the linear case, and I'm telling you that this is about state vectors evolving and solutions evolving, how come nobody's asked me where are these solutions evolving? Like I wrote down this thing, and I got a solution. But nobody's asked me the question, where are the solutions? What is the background space? What is the geometry? How come nobody's asked this question? Where do you assume the solutions are evolving? You should ask this question when you're given a differential equation, even in the non-systems case. Where is the solution evolving? I can write down the solution like I just put there, but where is this happening mathematically? Any ideas? So there's some hint here. I have some point that represents an initial state, and it goes to another state at some time t. So this is my space that I'm working with. I can represent, if I represent different states at different times as points in this set, then this could be a space of evolution, which I call the state space. So that's a question nobody asks ever. And it's the most important concept, actually. So, very abstractly now, if I just think of states of these systems as different points in some space, then this space, if you can imagine, contains every single possible evolutionary state of this system at any time t. Every point of the system. That's why we call it a state space. because this space collectively represents every possible configuration that your system of equations can be. So we call that a state. But then what is a state space? Is it Rm? Is it something more general than this? Any idea? Not a one. Okay. That's okay. I didn't expect you to know. What I call my state space in general is what we call the manifold. So I told you last time, to understand differential equations properly, you need to do linear algebra, vector calculus, and not topology. But I will do it nicely. I will not make it hard for you. I will try. Okay. But does everybody understand what I'm saying? So if I just generically denote this as my state space, then points in this space represent your system at any point in time. So sometimes it's here, sometimes it's here, etc. Yes?
Are the manifolds the things that have metrics or don't have manifolds?
Metrics give manifolds their structure, but in generic terms, you don't need to introduce the metrics.
For this, well, generally,
Uh,
doesn't necessarily have to.
exactly. We won't have. That's a good question.
But then, how would you know if it's a long collision interval?
Yeah, how would I know that?
Because didn't you kind of give it coordinates by saying it's x naught and it goes through x?
So we get to this. I've not actually told you anything about the distances between the two points. I need to introduce a metric on a manifold, but I'm talking about distances between two points. But I'm not doing it. I'm being more general. But does everybody understand what I'm saying? More or less. So this generic kind of space and points in the space represent my state of my system at any other time. So sometimes it's here, it can be here, it can be here. That's what I mean. But I want to quantify this somehow. It's too abstract. It's just a circle with some points in it. This is what we call a state space. And in general, a state space is what we call it. So I need to describe this. So let me do that. So I guess you can call this the idea of, actually, do I want to give it an idea? Yeah, maybe. Topological. Now, I assume you've not done this in multivariable calculus, correct? Topology, manifold. No, okay. Okay, so what do I mean by topological space? What does this mean? It's very easy. Do not get caught up in the terminology. The concept is actually very easy. So, consider a set M. So subset, call it M. And let me denote by T a family of subsets of M. So let me consider subset M, and by T I mean a family of subsets of M. So every possible subset of M, make it into a collection and denote that collection by T. Okay, and it's helpful to think of T, or maybe of M. M as a collection of points, as I just did it. So consider set M, which is the same idea as this set here. Okay. And T is a family of subsets of this M, so subsets of this, so something like that. So subsets of it. And M is helpful to think of as a collection of points. Okay? So that's the first thing to say. we denote the pair M comma T. We denote this as a topological space if the following things are true. Number one, the empty set, so this is not the flow operator, it's the empty set. So maybe I should write it with a diagonal line or something. Like that. The empty set. So everybody knows what I mean by empty set, right? I assume you've seen it. The empty set and M are members of T. Number two, the union of any selection of elements of T is also in T. So, if T is my collection of subsets of M, and I take a union of any subsets of those, that union must also be in T as well. So 1 must be true, 2 must be true, and there's another one as well. A third probability. The third probability. The intersection of any finite number of elements of T is also in T. So, if M in T is a topological space, if 1 is true, 2 is true, and 3 is true. And if these three things are true, then we say that the family / collection T defines what we call a topology. And further, the elements of T are called, very importantly, the open sets. Any questions about this? Just definition. It's not. Okay. So, given these facts, we will come now to perhaps the most important concept of this, and it's very simple. We could not do dynamical systems or any type of differential equations if what I'm about to write down is not true. And I mean the following. I define a neighborhood of an element. So remember, I said it's helpful to think of M as a collection of points. So an element of M is just a point. So a neighborhood of an element, call that element P. P for point, it helps you remember. Element P of M is a set, which I would denote as U of P, containing an open set for which, of which, P is an element. mean is that if I have some set here, and I have some point, I can draw an open set around P, which P is in there. This dashed line, if you remember from your calculus course, means open set around something. So that's what I mean by a neighborhood of a point. You see? So if P is my point, the neighborhood of this point is within some vicinity of some open set around there. Fine. It's not enough time. Okay, further than this, we say that my topological space M is, we call it connected, if it is not possible to write M is equal to, let's say, some set A union B, where A and B are elements of T, such that their intersection is non-empty. So A intersect B is equal to the empty set. They don't intersect. So, further, let me just, in the last minute, tell you where I'm going with this. So, if M is connected, then we can say that M is called what we call a special name Hausdorff. And what that means is, your manifold is Hausdorff, what that means is that any 2 points can be separated by distinct neighborhoods. In other words, so if this is my space M, and I have some points here, I can separate any 2 points by distinct neighborhoods. They never intersect. So I can draw that, and so. So if your manifold or your space is such that any 2 distinct points can be separated by neighborhoods and they don't intersect, then this manifold is called Hausdorff.
Master,
Yes?
if M is connected, M,
If M is connected, M is what we call Hausdorff, Hausdorff. And all that means is that any 2 points can be separated by neighborhoods. So you see the way I've drawn it is none of the open sets intersect. So that's very important. So all the manifolds that we will deal with in this course are Hausdorff. Yes?
Will the radius of the neighborhood be the same for all of them?
I can change. It doesn't have to be.
It doesn't have to be the same, but it should not connect.
It should not connect, exactly. Now, and the most important thing is that the open set should be a neighborhood of a point. So some vicinity, it does not matter what. It's an abstraction. Okay, I will continue with this on Monday. Maybe the first